Welcome to today's webinar. The topic today is Introduction to RFEM 6 interface with Grasshopper. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, German and English webinars, newsletters, and so on. I will be the moderator today, and I will answer your questions together with Lukas Sühnel. But my two colleagues can introduce themselves.
Hello, my name is Lukas. I'm working here as product engineer and customer support engineer with the focus on the interfaces. And as Andreas said, I will answer your questions today.
Hello, my name is Paul Sibolgin. I'm working as a working student at Dlubal Software. I support the product development in the area of interfaces, and today I'm going to give you the introduction into the Grasshopper interface.
Okay, thank you for your introduction. Then we can switch off our webcams so that the attendees can see the full screen. I say something, how you can ask questions, at least for the attendees who participate the first time. You can show that control panel that you can see on the right side of your screen. With that arrow here, and then you can enter the question here. You can also email your questions to info@dlubal.com after the webinar, and then you will get an email afterwards. Okay, then I hand over the screen to Paul. Paul, it's your turn.
Do you see my screen? Yes.
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 Yes. Okay. So start with the presentation. Let's have a look at the schedule for today. First, I'd like to start with an update on the latest implementation we developed for the Grasshopper interface, and then I'd like to show some basic information about the installation and the interface itself. And after that, we create a basic geometry in Grasshopper and define all necessary model and load data and export it to RFEM. So what are the new features we have implemented in the last time? First, when we're using the member component, we can now assign existing design properties to the member for steel and timber design. And these properties are not defined in Grasshopper directly, but we can read them from a template in RFEM. And we have also new components for the definition of imperfections, and at the request of a customer, non-linearities were also implemented in the line hinge component. And the next new features are that it's now possible to access the templates in RFEM via the export component. So for example, we can now define dimension design properties for steel and timber in a template in RFEM. And these defined design properties we can access with the member component in Grasshopper. And also the export of the polylines has been optimized, and we implemented the new components for closing and opening RFEM files in Grasshopper. Now I will give you a short information about the installation. The interface is not automatically installed. The installation must be done manually. It means with the installation of RFEM 6, you will receive a setup file, which is stored in the folder shown in this image. And you need to run the file, and the plugin will be installed for Rhino and Grasshopper. In addition, the web services must be activated in the RFEM program options, so that the connection between RFEM and Grasshopper can be established. And after the installation, we installed two plugins. plugin for the Rhino RFEM link. With this plugin, we can import and export data between Rhino and RFEM. We can import and export lines and surfaces, and this is limited to the pure geometry. So information about the sections or material thicknesses are not exported with this link. And in this webinar, we will show you the Grasshopper RFEM link. We have the import and export option as well, with the focus on the export to RFEM components. And the import works in such a way that we are able to read the information defined in RFEM and use it further in Grasshopper. We can export model data like sections, member, thicknesses, hinges, materials, and also supports, as well load cases and load combinations, and also the loads. And the result import works by allowing us to start the calculation from Grasshopper and read the results from RFEM automatically back into Grasshopper, and then we can save them as a XML or a CSV file. The results can also can be further used, for example, to perform optimization calculations for various extensions in Grasshopper, like a geometry or section optimization. Yeah, that's for the short overview. So what can the Grasshopper interface be used for in general? First of all, the Grasshopper interface is an alternative for the model generation. We use the plugin when we don't want to enter the model manually into RFEM, but we want to model algorithmically in Grasshopper or generate a structure with various tools in Grasshopper. Another strength is the ability for the parametric model generation, so that you can make parametric changes to your structure without much effort and without having the entire time-consuming model adjustments. You don't have to adjust the model manually. Yeah, and this is useful, for example, for variant studies or optimizing structures in general. Yeah, and now we're going straight to Rhino and start Grasshopper. In Rhino we have this icon, and here we can start Grasshopper. If we start Grasshopper, we get a 2D script environment, and on this environment we have different components we can put on. So for example, we have components like this, where we have an input and an output, and we can connect these components to each other to create algorithms and build parametric models. And once the plugin is installed for Grasshopper, we see a Dlubal tab here, and there are 3 groups available in this Dlubal tab. We have a tab, one group for the model data, like member, section, material, surfaces, openings, and so on. And we have a second group for the load data, like load cases, nodal loads, support loads, also loads by themselves, and also design situations, static analysis settings. Yeah. And in the third group, we have the export component and other components related to the import. We only need the export component today, and I will go more into detail about this one at the end. And what's the plan for today? A little preview what we're going to do today. And we want to model a small structure and then assign to this structure the model data and load data with the help of the RFEM link. And afterwards, we want to export the model to RFEM. So we assign materials, sections, members, nodal supports, load cases, and loads. And we're gonna start today with the geometry in Grasshopper. So we start with a new project, and we like to generate a truss girder. So I shared the screen with Rhino so we can see how we generate the model in Grasshopper. And to do, if we start with, as we want to, as we're going to generate two lines and the x-axis, and between these two lines we want to generate the truss. And first we start with a point. First we create a construction point using this construction point component, and afterwards we want to copy this point by holding down the Alt key. Now we have generated 2 points, and for the second point we want to set up a number slider for the x coordinate, so we can adjust the x coordinate with the slider. So we can double click on the canvas to generate a slider between 0 and 15. Now we can connect it to the input of this construction point component. After that, we want to create a line between these 2 points. See, this is the second point we created. And we want to create a line between these 2 points. And for this, we use the line component. You can click the canvas and write the name of the component, or you can also find the component in the curve tab and grab it from there. So we need a start point and end point in the input of this component. So we have these 2 points, and now we can generate a line between these 2 points. Our next step is to copy the line with the move component. And here we have to input the geometry and the motion. The motion is by default set to 10 in the Z direction, but we want to define it ourselves. And so we need at first the direction we want to move the line in. And also we can set up a range again with a number slider. So we want it to move from 0 to 5 in the Z-axis. And if we connect it to our moved line, we see the second line appear here on the screen. And after this, we want to create or generate a truss between these 2 lines. And for this, we use the lunchbox in Grasshopper. And here we have different options to generate a structure. We want to generate a 2D truss between 2 curves. Our curves are now here the lines we're using. And between these 2 lines, we can generate this truss. And for this truss, we can set a number slider for the divisions. That's the number of bays we have in this truss girder. So we set up again a number slider, and now we can control the number of divisions or the number of bays in this truss girder. So that's our structure. As an output of this generator, we get different outputs. We have the primary lines, that's the lines for our upper chord and our lower chord. We get the lines for the diagonals, and we get the vertical lines, and we also get the points of our structure. So and we want to apply now the model data and the load data onto the structure. And yeah, for this we use this components from the Dlubal tab. And first thing we want to do is to define a material. And if we defining a material, we have two inputs. First input is the material number. This is the material index we gave the material in RFEM. We can set it as number 1. And the material name can be defined with a panel. So we can say we have this material name here and just put it in the component. But we want to use several materials for this example or just a possibility to use several materials without having to change the name every time in this component. So for this we can create something like a material library. I copied this from another Grasshopper file. And this is also just a simple panel with the material names inside we often use. And we can now use this index number in this list to define the material names. And we're doing this with another component, with the list item component. And with this component, we can retrieve a specific item from a list. And we can access the index number with a number slider. So we have here both material names. So we generate a number slider between 0 and 12. And in the output, we receive now the corresponding material name. I will quickly show this. So now we can access every material name we defined in this list. Yes, and this will, this was too much. And this will be the input for our material name. And that's all for the material. We have now defined the material, and after that we want to define the section. So again, in the Dlubal tab, we have the section component for this. And the section definition is just like the material definition. So we can copy this here and set, we want to set two sections, one section for the upper and lower chord, and one section for the diagonals and the vertical lines. So we have section number 1 and section number 2. I predefine it here so we can copy it afterwards. And the section name is assigned like in the material component, but we use here a different list. We use here a list for the section names. So, and now we have defined one section. We can look at the input. Further the input, we have the material number. We have to assign the material number. And here we can take the material number from the material component and assign it to the section component. So we can transfer this number to this component. We have more inputs possibilities. For example, we can define the rotation, section rotation with an angle, and also user-defined section values. And if we want to copy, we want to define two sections, so I can copy this component, and this will be our section number 2. So let's set it to the APE 100, and here we set it to the HAR 100. If we have defined this section, we can define our members, and these are the members we will assign to the lines of our structure. And here it makes sense to have a separate member assignment for the upper chord and the lower chord, because we only want to apply a load on the upper chord, and it will make easier later to distribute the load on this upper chord if it's defined in a separate member. So the first input of a member component are the Grasshopper lines from our structure. So let's look back at our structure, move it a little bit. We have lines for the upper and lower chord. So we can, here we see a list with all, here we get a list with all lines for the upper chord and lower chord. And we want to remove the elements from the list, so we only get the lines for the upper chord. This we can do with a call pattern component, and this component removes elements from a list using a specific rule. So first of all, we need to know which index numbers in this list assigned to the upper chord, or which numbers represent the upper chord. So we can look at the index number with the item list component. So we look at this list and can look on with a number slider at the different index numbers. So we see here the line with index number 0 is line from the lower chord. The line with the index 1 is the line from the upper chord. Index 2 is again the lower chord, 3 the upper chord, and so on. So we can set here a rule to remove always the first item from the list and keep the second item from the list, and repeat this rule for the rest of the list. So we only get the lines for the upper chord. So we can set this, realize this with this call pattern component. We can set a rule in this component. So we can say we want to keep, we do not want to keep the first element in the list. So we set this false for the first element. And then we ask, do we want to keep the second element in the list? We say yes, we set this to true. And after that, the rule will repeat itself for the entire list. And with this, we get only lines for the upper chord. And now we can copy this component and invert the rule, so we get the lines for the lower chord. And this allows us to separate the member assignment for the upper chord and lower chord. So we define two member components, and this will be our upper chord member, and this will be our lower chord member. And the next input in the member component is the member numbering. This is an optional setting, but it's optional setting, so the number assignment is done automatically in RFEM depending on how we connect the components with the export component. But we need a numbering for the upper chord because loads are assigned to this upper chord members, and the member component we use later requires member index numbers the load is assigned to. And for this, we can make a simple list for our numbering, like 1, 2, 3, 4, 5, and so on. And now we can connect this list to our member component. The problem is that the number of lines we have here must match the count of the numbering we define in this list. So every time we modify the structure here, the number of lines also changed, and we have to adjust this panel or this numbering in this list every time we modify the structure. So we need another solution for this problem. So we can generate the numbering differently with a series component. A series component creates us a series of numbers, and we can start the numbering with 1, and the number at step size for the numbering is also 1. And the number of lines we have is equal to the number of truss base we define here. So we can connect this numbering to the count of our list. So we receive always the same, or always the correct numbering of the upper chord lines. So we have here 9 lines. So if we modify this truss, we always get the correct count for our members. So this will be our member numbering for the upper chord. So let's have a look at the member definition in RFEM. So I can introduce you to this component. Here we have an optional setting for the section distribution. It's by default set to uniform, and we can define this with a value list. You see here, you can define it with a value list. Value list is just a list where we connect it with the import, and we get a list with the possible section distribution we can use. Here's also a comment that only uniform and linear are supported for now. So we only use this uniform and linear, but with this we can modify the most sections we often use. And if we don't put an input in this section distribution, we get as a default settings the uniform section distribution. Also, we need to assign a section at the member start. It's also like in RFEM. And we also have the possibility to assign a member rotation with an angel, with a help node or a surface. And for this, we have these inputs here. And the Grasshopper component also allows us to define hinges or eccentricities for the member. So the only input we here need is the section start. So we can connect one defined section with our member. And with this, we have a completely defined member for the upper chord. For the lower chord, we use the same member. And here we do not need a numbering because we do not want to link it any further with model data or load data. So this will be assigned automatically in RFEM afterwards. So we also assign a section start, a section at the member start. So we choose the same section. And for the diagonals and the vertical lines, we also generate a member. So we take this Grasshopper lines, connect it to our member, and we take this Grasshopper lines. You can hold down the Shift key if you want to put several information in one input. So we have here two informations for our Grasshopper for member input. Do I connect? Yes, okay, it's connected. Yeah, and The second section is for our, we define a different section. We define this section for our upper chord member and lower chord member, and for the verticals and diagonals, we define a different section. Okay, afterwards, we going on with the support for our structure. We can assign a nodal support, a line support, or a surface support. The structure, we need the nodal support. So we want to define two nodal supports at the edge of the lower chord, and these points we also get from our structure, and these are the construction points we use to generate the structure. So we can easily assign these points by holding Shift key to this nodal support component. And the numbering, we can also use number of nodes as alternative to the Grasshopper input, but here we use the Grasshopper nodes. Next, we defined support conditions. We can define a number. With a number, we can define a string. 0 means 3, and when we use the expression inf, we can define rigid support condition. Here we want to define a hinged support. So we defined the support conditions for hinged support, and we want to prevent the x-axis rotation. And we have here some more inputs. We can now look at this again in RFEM. So if we define a support, we have here some optional settings for non-linearities, for failure, or for friction, and we can define the friction coefficient also in Grasshopper. And we can set the rotation for the nodal support. And here we have different direction types, and we can set a rotation with one of these direction types, rotated by angle or alignment on a member, node, or line. But this input we don't need. We don't need in this webinar. So that's everything we need to define our nodal support. And afterwards we can go on with our load data. As the structure is so far finished, and now we can generate load cases and loads. At first we define two load cases. For this we'll use the load case component. Here we can assign a load case number. We will generate two load cases, so assign load case number 1 and number 2 to copy it afterwards. We have load case name. This we can define again with a panel. Let's name it permanent load, for example. Let's make the panel a little bit smaller. And just like in RFEM, we first defined the static analysis settings and the action category. And we can look at this again in RFEM, so it's easier to follow. Here we have, if you generate load cases, we have the static analysis settings. And for these settings, we use a separate component in Grasshopper. So as you can see, now you can see the static analysis settings. So here we have the option to give again a number, and we have the possibility to set the analysis type like linear, second order for the analysis type for large deformations. And when using tension members, we have the possibility to activate this exceptional handling for failing members so that you don't get an unstable model due to tension members. Do you find this option here if the tension member is activated in the model? And also we can modify or have an optional input for the number of iterations and the number of load increments. And this is some input for the form finding iteration for the form finding add-on in RFEM. So let's define this static analysis settings. First, we give it an index number. That's number 1. The analysis settings are defined by the value list. So we can generate a value list and choose between the options we have here. The other inputs are not necessary for us. Now we can assign the static analysis setting to our load case. Now we're missing still the action category, and the action category is a separate component in RFEM, in Grasshopper, and these components allow us to define a standard group and select like the EN 1990 and allows us to select the corresponding action category for this standard group. Here it is important to note that the standard must be also activated in RFEM in the base data. So if you use the standard in Grasshopper, make sure you have the same standard active in your RFEM file. So we can disconnect again our load case component. And here we have some more definitions for, or some options for self-weight adjustments with a factor and the direction of the self-weight. And for the first load case, the self-weight is automatically activated in RFEM, so we don't define or don't add input here. Now we want to copy this load case. And set it to the load case number 2 and change the name to imposed load. And also adjust the action category to imposed loads. So that's the definition for our load cases. And after the load case is defined, we want to apply the loads. We want to apply a nodal load on the nodes of the upper chord. And we also want to apply a member load on the members of the upper chord. The nodal load component, we can again define optional index number for the load. We can assign the load case to this nodal load. So we have here one load case number 1 and load case number 2. And here we first need to assign the nodes the load is assigned to. And for this we have our structure where we find in the output a list with all nodes of our structure. And again, we only need the nodes from the upper chord. And with the point list component, we can easily see the numbering of our nodes. So you can define the size of this points. So here you can see that we can display the numbering of the nodes directly in Rhino, and we want a load on all odd numbers here at the upper chord. So the problem here is that RFEM assigns a different node numbering than Rhino. Rhino starts the numbering with 0, and RFEM starts the numbering with 1. So if we want to assign the node loads to the correct nodes in RFEM, we need to define a node numbering so that the numbering of the upper chord nodes in RFEM matches the numbering in Rhino. So that means we have this list of nodes, and we want to extract the odd numbers from the list. This is possible again with the list item component, where we take this list and we want to extract the odd numbers from the list. And to do this, we need a series component to create a series of numbers. This we use again the series component, and this series start again with the number one, and the step size is now 2, so we get all the odd numbers. And the output you see, we get number 1, 3, 5, 7, 9, 11, and so on. And the value of the nodes we like to number is always 1, 2, 3, 4, 5 nodes we like to number, and this value is always 1 more than the number of class base we define. So we can again use this parametric number and add 1 to this number. So we can do a simple addition, and so we take then the number of the class base, add 1 to this, and this will be the count number for our nodes. Let's make some space here. So the series, we can connect the series component to our item component, and now we see that we got only the odd numbers on nodes for the upper chord. And these nodes should receive the same node numbers in RFEM, and for this we create a node component, and after this we can say these Grasshopper nodes will receive the same node numbering in RFEM, and the node numbering we defined in the series component. And these nodes are now assigned to we can assign to our node load back here. So there are some other inputs we need to fill. We can look again at the new node load in RFEM. So if we define a load in RFEM, we have to define the load type, the coordinate system we are assigning to, and also the load direction. So that's the same in Grasshopper. So for example, we also can define different load types, and for this we also have the further inputs for the load types definition for the parameters we use in RFEM. So we need a normal force, so we only need one parameter here. If we start defining the load type, we see it's again a value list, So we can again define a value list for this. We define a simple force. The coordinate system is, we can referring to the local coordinate system with the expression local, or we can refer to the global coordinate system with the number 1. We're using the global coordinate system, and the load direction is again defined with a value list. So we can set the load direction in global Z direction. And at the end, we need to define the force. Here is the force defined in Newton. So let's define 3000 Newton as our nodal force. So that's all for our nodal load. After that, finally, we want to apply a member load on the members of the upper chord. For this, we'll use the member component. Here we have again an optional input for the member load number. We assign our second low case to this member load, and the member index numbers the load is assigned to are already defined for our upper chord. So we take them from our member component. So we have here a definition for our member numbering, and we can take this member numbering for our member load. The other inputs are again the same as in RFEM. We define a load type, a load distribution, coordinate system, and load direction. Let's look at it. So when we insert a new member load in RFEM, the load type is set to force by default, and the load distribution is set to uniform by default. And the same logic applies also to this Grasshopper component. So if we don't give an input to this load type and load distribution, it's assumed to be the default setting, and here it's the force and uniform setting. If we want something different, we can here use the value list to define other categories for the load type and load distribution. Here we see also different inputs for different load types. So depending on the load type we define, or depending on the load distribution we define, we have here the different parameters we need to access. And here you have the possibility to access most of them. Not all load types implemented. The most commons are available. So with this, we want to keep the input of the components, or the input of the components remain manageable if we don't add every single parameter to implement. And so the only thing we need to input here is the coordinate system. We refer again to the global coordinate system with the number 1. We can define a load direction again with a value list. Load direction we define as global Z in the true length. And we define the load magnitude again in Newton per meter. Let's say 2000 Newton. And with this, also the member component is ready. A member load component is ready. And now we want to export this data to RFEM. For this, we use this export component. And first, we need the export component must be connected to the defined data So we need an input for this component, what we defined also input for the model and the load data we defined. So we have the material, the actions we defined, the members we defined, also the nodes here, our nodal support, the static analysis settings, our load cases, and finally also our loads. So we can run the export once with a button. For example, like with this button, we can run the export once with the button, or we can use a Boolean toggle. And with a Boolean toggle, we can create a live link between Grasshopper and RFEM. So we can set it off true, and the connection remains active between Grasshopper and RFEM. So if I adjust the parameters in Grasshopper, like here, if I adjust some parameters in Grasshopper, the RFEM model will be automatically updated as long as this Boolean toggle is set on true. As there are some other settings we need to inputs we need to fill. So we want to overwrite the model in RFEM, and we also want to flip the z-axis. If we want to generate a new model in RFEM and don't overwrite a model, we can also define a model name, and a new model will be generated in RFEM. So let's look at the export in RFEM directly. Let's move RFEM on the screen so we can see the export. I will delete all data in this file here. And if we set the Boolean toggle on true, the export will be started. Okay, I forgot something. Maybe we're missing the lower chord. So we can check if we connect the member with our export component. Why is the lower chord missing? The member is missing for the lower chord. Let me check this. Okay, this is the lines for our lower chord, and we don't adjust them to our member. We got the wrong input here. So as you can see, we have a live link. So if we change here something, okay, we have the wrong assignment for the diagonals and the vertical lines. I will correct this fast. Can disconnect. This was connected to our upper chord. You see, if I work on this model, also the RFEM model is updated. So here we have the lines for the diagonals. Set it in this input and see the update. And we have here the lines for the vertical lines. So now it should be correctly. Yeah. So we have now exported the model to RFEM. You can see the structure is exported, the supports are defined, the load cases are defined, load case 1, load case 2, and also the load is assigned. Now you can continue working with this model in RFEM, start a calculation, create load combinations, or start analysis or design calculation. Yes, and so that was the basic introduction into the Grasshopper RFEM interface. I thank you for your attention, and now I hand back over to Andreas.
Okay, thank you, Paul, for this presentation. I would like to show you where you can find or where you will find the recording in the next days, and the Grasshopper file and the RFEM file. I hand over the screen to mine, just a moment. Before I would like to show the website, just a small hint. If you want to book your free online appointment, such as a product demonstration or something like that, just contact our sales team with that link here, or you can scan the QR code. You can also get a non-binding offer from them if you want. Just contact them. You can also download the PowerPoint slide from our website. I will show you where you can find all. That's our website, dlubal.com, and under news and events, you can find the webinars. That's today's webinar, and those are the future webinars, and you can also find the accomplished webinars. We record all our webinars. So I click on that webinar from today. You will get an email in the next days with a link directly to that page, and then you can find the recording in the middle here. You can already find the presentation slides, the Grasshopper file, and if you scroll down, you can download the RFEM file. Okay, that's also all from my side. Thank you for your attention. Thanks to Paul for the presentation. Thanks to Lucas for answering the question or questions. I wish all a nice rest of the day. Maybe we meet each other in a future webinar. Bye-bye.